Oh, good. Whoa. Like almost hitting my knees on the table. All right. Let's change this here. 20. Hey, leap day tomorrow. What's gonna happen? That's crazy. Is he like 10 years old or?
He's 18.
Oh, that's pretty good. That is so, it's crazy. It's crazy, but it happens. Okay. So, did you guys have a look at the long division, dividing polynomials? Let's practice some more. That sounds good. Yeah. Did you guys get a chance to look at the synthetic division? What's kind of tricky about the synthetic division is it only works when you're dividing by x minus c. And so it's pretty limited in terms of what you can use as your divisor. And so we'll call this kind of review, but I'm not sure I got to mention it last day, so here we go. Long division can be used for any dividend p of x and any divisor q of x, sorry, d of x, q is the quotient, d of x, okay, in something like p of x over d of x, right? Whereas, I'll put a little arrow here, whereas for synthetic division, right, d of x is going to have to be in the form of x minus c. So for synthetic division, can only be used when d of x is in the form x minus c, right? So x minus 1, x minus 2, x minus 3, right? X plus 1, x plus 2, right, for negative c's. So it's very kind of limited and not very useful, right, in terms of long division, which we can use all the time. So that's why we're going to focus on long division. So synthetic division can only be used when the divisor is in the form x minus c. Okay. For this reason, we will focus on using long division, right? Just so we know. And I think I mentioned it last day. So long division of polynomials, and even just as I was walking over here, I got caught up talking to Jason, who's teaching Calc 2 right now. And he's like, oh, where are you going? I'm like, oh, pre-calc. He says, make sure they do long division of polynomials. I was like, well, actually, we're doing that right now. And he was like, oh, good, because they get to Calc 2 and they'll tell me they've never seen it before. And he's like, but we really need it. So it's not until Calc 2, but then in Calc 2, then you'll use it again. And of course, you'll have to brush up on it, right? But at least you'll have seen it. You'll remember me saying something about, oh, I think we need it in Calc 2, right? So, so let's do some problems. Right. Can't remember which ones did we do last day and which ones should we do? Should we do, let's see here. Should we do, should we do maybe 12 and 14 or something like that? Because they're evens, right? Kind of picking from the higher number ones. So let's do number 12, where P of X is 4x to the 3 plus 7x plus 9, and D of X is 2x plus 1. So I'll clean up this X here. So if we write it in the form of 2x plus 1 going into 4x to the power of 3 plus 7x plus 9. Well, I guess I'll need a little bit more room up above because that's where my quotient goes. So what we did, right, was we said, okay, I have to take the first term of my divisor and divide it into the first term of my dividend. And then the result goes up here. And then I take that and I multiply it by this whole thing and put it down here and subtract. Right? So a little bit of machinery here. Right? But once we get into the groove, it's okay. So 4x to the power of 3 divided by 2x. So if we do it on the side here, right, 4x to the power of 3 divided by 2x is going to be 2x to the power of 2, right? Now, whether you just cancel the powers here, right, we've got x to the power of 3 and x to the power of 1, right, 3 minus 1, or if you actually bring up that x, it doesn't really matter. At this point, I'm assuming that you're comfortable kind of canceling to get to this point. So we get 2x squared up top. And so here, 2x squared. Good. Or no? Yeah. So now we take the 2x squared and we multiply it by 2x plus 1. And we put the result down here. Oh, I think that's what you were trying to say. I have to make an x to the power of 2 in here. Forgot. Why? Because we have to have, so we've got x to the power of 3. I have to have a slot for x to the power of 2 so that when I get 2x squared times 1, I have to have room for it. A little rusty.
Would that just be like 0 to the power?
Yeah, so it's going to be 0. So I have the luxury of just scooting these guys over a little bit here. Lucky me. Looks like nothing happened. Plus 0x to the power of 2. Now I've got x to the power of 3, x to the power of 2, x to the power of 1. Technically, x to the power of 0, right? Anything to the power of 0 is 1. Good. I missed our first step. So now, if I use the same color just to kind of indicate, so then I have 2x squared times 2x makes 4x to the power of 3. And then 2x squared times 1 puts me at plus 2x squared. Oh, turn my square into a triangle, ironically. So now, right, I have to subtract here. So minus these guys. So 4x to the power of 3 minus 4x to the power of 3 makes 0. Making sure that this minus is actually outside brackets. But just to keep it nice and clean, I'm just going to remember that I have to subtract, right? So if you want to, you can put brackets around here, but you don't have to. I'll do it for this line, but I won't do it for the next few lines. Okay. So 0x squared minus 2x squared puts me at minus 2x squared. Whether you want to move all the 7x plus 9 down, that's fine, because you could do that. You could say 7x minus 0x is plus 7x. Plus 9 minus 0 is plus 9. Right, so you could shift them all down if you want to. But for me, when I'm showing you guys, what I'm going to do is I'm going to keep them up here, and then you'll see that things kind of cascade down. Right? But however you prefer to do it is fine. So now I'll use a different color, because what we're going to do, right, is we're going to do the same thing from here, right? And that's when it might be nice to have these brought down, because now you're taking 2x into the leading term of this guy, right? Kind of ignoring this for a little bit and only working on this. So now we have 2x going into negative 2x squared. So I've got, I'll do this one in green, negative 2x squared divided by 2x is going to be negative x. X squared and x are going to cancel to 1x, and then negative 2 over 2 makes negative 1. So now I have minus 1, which I can put up here, say minus x. Now I take that minus x and I multiply it by 2x plus 1 and put it down below here. So then I get minus x times 2x. So I get minus 2x squared. And then minus x times plus 1 puts me at minus x. Again, I'm subtracting this whole thing from the top. And yeah. So I've got negative 2x squared minus negative 2x squared. So that's plus 2x squared. What you'll notice, right, because of how we've set up these values, this first number should always go away. Right? So if it's not going away, then something happened and you have to go back and look at it. Okay? But now this 7x is the one, so 7x minus negative x plus 8x. Right? But just remembering that you're pulling down that 7x there. So I'll just do kind of a dot, dot, dot down there just to show where it's coming from. But 7x minus negative x plus 8x. And now we do it again. All right, put 2x into 8x, but this is the last time that we're going to do it, right? Because then after that, I have no more x's to divide by, right? So once you hit the highest power here, down here, then that's going to be the end. The rest will be remainders. So we've got 8x divided by 2x which is going to be just 4, right? The x's are going to cancel. 8 divided by 2 is 4. So then we have plus 4. And doing the same thing over again, right? 4 times 2x is 8x. And then plus 4 times 1 is plus 4. Nice. And keeping in mind here that we are subtracting still. So now I've got 8x minus 8x is 0. And then I've got 9. So again, this little guy is kind of tracing down that way. 9 minus 4 puts me at plus 5. So this means that this plus 5, this here, let's see if I can find a color. This here is the remainder. Right. The remainder is still being divided by 2x plus 1 because I can't put any 2x's into it, right? And so the remainder is actually 5 over 2x plus 1. Yes?
If the quotient have the value of 2x here plus 2x plus 1, then the answer will stop over there when the highest value
Exactly, is x squared.
8x here
Yes.
plus 9.
So here, if this was 2x squared,
Yeah.
then we would stop dividing at this point.
Yeah.
Right, because then we've got our x squared, and
The remainder.
just like we stopped here when it was x over x,
Yeah.
right? Then if this was x squared, we'd have to stop at x squared over x squared.
Yeah.
Right, which means we would stop here.
And then the remainder will be 8x plus 9.
Yeah. And we're gonna do one like it when we do 14. Is that good? So here,
This is what we have done on that day, because
it's a lot. So depending on how you want to write it, right? The questions 3 to 8 on your handout. Did you get a handout? Yeah. Okay. Good. 3 to 8 want the answer written as p of x over d of x. Oops. P over p. P of x over d of x is q of x plus r of x, oops, over d of x, right? Or same idea, right? P of x can be broken down as d of x, q of x, plus r of x. What have we done here? We've just multiplied the d of x over to the right-hand side. It's canceled here, but now we've got q of x times d of x. And so these are the same, right? We've just multiplied the d of x over to the right-hand side. So to me, it doesn't matter which way you want to write it, right? But for us, how about, right, I'll write a little note here. These are equivalent. And maybe I'll even justify it down here. So many arrows, crazy. Since p of x over d of x, if it's equal to q of x plus r of x over d of x, that's the same as p of x and then d of x times all of that q of x plus r of x over d of x.
So when we're writing the answer, would we multiply it out or will we keep that?
No, whichever way. So I would probably tell you in this form or in this form, and then you can just plug them in.
Okay.
Right.
So we wouldn't multiply the d of x into the q of x.
No, you wouldn't have to. I'm just showing how these two are equivalent. So it's just to tie it all together. And so now if you've got p of x on this side, then you've got dx times qx plus rx, oh sorry, I'll put it on this side, d of x times r of x over d of x. But because we're multiplying, these cancel. And then we're left with d of x, q of x plus r of x. In the one that we just did, right? Kind of labeling this stuff. This is our d of x. This is our q of x, the quotient. This is our p of x. And the remainder is the r of x.
Just 5 or 0 plus 5?
Just 5 usually, yeah. Because see how we've got zeros all along here, but when they're, we can just ignore them. Yeah.
Same as in p of x, we can just not write the 0x squared again.
Yeah, you could skip this one if you wanted to, because it wasn't in the question. We needed it so that things would line up, but it's not part of the actual p of x. If you put it there, that's fine. There's no harm in putting it there, but if you don't want it there, you don't have to have it there. Good, nice. So either way, how we arrange this, using whichever kind of summary, as long as you remember which one's your q of x, which one's your r of x, p of x, d of x, you can use either one. And I'll tell you, like I won't say, oh, use the second. No, that doesn't make sense, right? It's just a matter of if we want to rewrite it as, so if you want to rewrite your polynomial, right, as essentially something factored, right? Here it's factored versus, oh, yeah.
I was just going to ask if we would, if it can be factored further, if we would factor further. Like if the 2x squared minus 6x plus 4.
You could probably factor it further, but unless the question says factor this, I would just leave it. Yeah. But if your goal is to factor things, right, then writing it in this form would be the most helpful, because then you've already split out the d of x, 2x plus 1 times 2x squared minus x plus 4, and then if you can factor that even further, then that's great. Right, and then plus 5.
Okay, but unless it's specified in the question, we would just stop there.
Yeah, then it's like, you've done enough. Yeah. Yeah, definitely done enough work. Right, and so in our case, right, if we say p of x is d of x, q of x plus r of x, in our example, I'll put it in the middle of the page actually. In our example, our p of x was, oops, 4x to the power of 3 plus 7x plus 9, which is d of x, which is 2x plus 1, times q of x, which was the 2x squared minus x plus 4. And then plus r of x, which is 5.
And will we ever multiply it out, or would that be counterproductive at that point?
Well, I mean, you could multiply it out to make sure that you get to the original polynomial to check your work. But no, not. But it's good to check your work, right? If you're not sure.
I guess that would just be saying that 4x cubed plus 7x equal to 4x cubed.
Which is like, right? But here, right, one thing to notice is that it's factored, or at least more factored than when we started. Okay. Any questions about that one? Should we do 14? Because it's looking very tricky. And I'm a little bit scared because I haven't tried it beforehand. So, and I haven't, well, this one turned out okay, I think. Going in blind, feeling cocky. I can do long division, no problem. Under pressure and everything. Hopefully all these are divisible by 3. Otherwise I'm screwed. 14. Looks like they are. If p of x is 27x to the 5 minus 9x to the 4 plus 3x squared minus 3, one thing that I will do while it's still fresh in my mind is I'm going to write out the expanded one with all of the x's, right? And so here below, just to make a note to myself, if my highest power is 5, I have to have a power of 4, 3, 2, 1, and then 0. So I've got 27x to the 5 minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. So that's the one that I have to work with. And we're given this huge d of x is equal to 3x squared minus 3x plus 1. Here we go. So what's this going to look like? I think I'll scoot it so it's on the same page. Don't want to have a page break in between. So I've got 3x squared minus 3x plus 1 going into that huge expanded one with all the powers, right? 27x to the 5 minus 9x to the 4 plus 0x to the 3 plus 3x squared plus 0x minus 3. This would be very difficult to deal with, right, if we didn't have long division, right? So here we go. You guys ready? First term, 3x squared into the first term, 27x to the 5. Now, I don't have room on the side to write it out, and so, but we did the nitty gritty one, so here we go. I'll still try to use colors, but who knows. 27x to the 5 divided by 3x squared. Now, there. 9x to the power of 3. Now, if I do 9x to the power of 3 times 3x squared minus 3x plus 1, I get 27 x to the 5 minus, is it 9 times 3 is, oh, again, minus 27 x to the 4, and then plus 9x to the 3. Subtracting these, 0. -9 plus 27 puts me at plus 18x to the 4. 0 minus 9, 9x to the power of 3. I'll let you kind of work away a little bit, but I'll keep going here. 18x divided by 3x, or x to the 4 divided by 3x divided by, so I get plus 6x squared. 6x squared times 3x squared, 18x to the 4 minus 18x to the 3 plus 6x squared. Zero, negative 9 plus 18 plus 9x to the 3, and just to indicate that that 3x squared comes down, so we get 3x squared minus 6x squared. I get minus 3x squared. Okay. Nine x to the 3 divided by 3x squared puts me at plus 3x, and that's it. 3x squared times 3x, 9x to the 3 minus 9x squared plus 3x. Bring this 0x down. Oh, 9x to the 3 minus 9x to the 3 is 0. Negative 3 plus 9 plus 6x squared. 0 minus 3 minus 3x. One more color here. 6x squared divided by 3x squared plus 2. 2 times 3x squared, 6x squared. 2 times negative 3x minus 6x plus 2. Good thing too, because I'm out of room here. Zero. Negative 3 plus 6 plus 3x minus 3 minus 2 minus 5. We did it. Because now this is our remainder, 3x minus 5, right? So if we had to put it in terms of r of x is 3x minus 5, because my highest power here is 3x squared, and so I can't put it into 3x anymore. So in terms of the question, right, P of X, we said was 27 x to the 5th minus 9x to the 4th plus 3x squared minus 3. D of x we were told was 3x squared minus 3x plus 1. And then we found that Q of x is 9x to the 3 plus 6x squared plus 3x plus 2. 9x to the 3 plus 6x squared plus 3x plus 2. And R of x is 3x plus 5. Just checking.
Isn't it also
Tell me. Tell me. And then whichever way we want to summarize it, right? It doesn't matter because now we have them. Right. And so now what we could do is we could summarize this thing, this huge thing, right? Something to the power of 5 as this times this plus this. Which is really nice for just being able to factor stuff and potentially canceling stuff. Any questions about that one? No. Let's do it. Let's do it. Which one? Which one? Which one? Which one? How about we do? Huh?
That's easy.
Number 8. Which one do you want to do? 10? You got it. Let's do 10. Okay. So 10 tells us that P of x is x to the 4th plus 2x to the 3 minus 10x. D of x. Oh, actually, I kind of like doing the spreading it out first. I don't know. It's a good way to remember it because remember I forgot to do it in the very first one. I'll blame it on being rusty. 2x to the 3 plus 0x squared plus 0, or no, we've got an x minus 10x, but then plus 0. And then d of x is x minus 3. Okay. Put this on one page. X minus 3 into x to the 4th plus 2x to the 3 plus 0x squared minus 10x plus 0. How about we do this one alongside each other? So try it. I'll work on it up here, and then we can check in at the end. Bless you. Bless you. Now I'm so curious. Did we get the same thing? Hey, I'm wondering.
We're not going through.
Yeah, it's like, okay. Yeah, it's like, big guys, I got x to the power of 3 as your quotient. So up top here, x to the power of 3 plus 5x squared plus 15x plus 35.
Yes.
And a remainder of 105.
Yes.
Nice. Okay. That is really good. Really, really good. It's huge. All right. So, how can we use this besides factoring, right? Besides pulling out x minus 3 from this thing, for example, right? We can use there's the remainder and the factor theorem. So, first we're going to talk about the remainder theorem. Actually, I'm just going to steal the blurb from your handout, I realized. 3.3 here. Copy. Oops. So it says synthetic division, but obviously we can use long division, right? It's the more powerful of the two. And so here I'm going to write and long division. Right. Synthetic division was special to having the divisor of x minus c, where c is some constant. So the remainder theorem only talks about x minus c. And so if you've got a polynomial, so that p of x that we've been dealing with, divided by x minus c. So the one that we just did, for example, we had x minus 3, right? So in the previous example, d of x was x minus 3. So c would be 3 in that case, right? Then the remainder, that 105 that we found, now this is kind of like a weird trick that you can use. The remainder is p evaluated at c. That's weird, right? So what it's saying is that our remainder, right, r of x, we said that r of x in our case was 105. And the remainder theorem says, that since c is 3 and r of x, the remainder, is 105, the polynomial evaluated at x equals 3, right, p of 3, must be 105. We can check this, right? P of x, remember, was what? That's right. Yeah.
Then the answer will be 105.
Which we'll check, right? So here, p of x was x to the power of 4 plus 2x to the power of 3 minus 10x, right? That's the one we just did, yeah. P of 3 is when we plug in 3 into here. So we have 3 to the power of 4 plus 2 times 3 to the power of 3 minus 10 times 3. 3 to the power of 4 is 81, plus 3 to the power of 3 times 2, 54, minus 30. So 81 plus 54 minus 30. All right. So I don't know when you would use it. You would have to have a really, really huge p of x where you think it's going to be faster to use long division to figure out what the remainder is than to plug it into here, right? But what it does tell you is it gives you a nice way to check to make sure that you got the right remainder, right? So that you can check your work.
If we get a question like this in the quiz, then we can use this formula.
That's right. Yeah. So, right, and so the remainder theorem says that as long as you're dividing by something that looks like x minus c, right? So it has to be in the form of x minus c. So even if you're doing x plus 2, for example, your c would be minus 2. Right? But it can only handle x minus c. And so this portion of it is really important. Right? Only x minus c.
Yeah, x plus c, you can just make the negative c though.
That's right. Or x plus c is x minus negative c. But it can only handle those little cases. But if you have a look through your the problems that are on the first page, right? Number 3, you could do it for. Number 4, you could do it for. Not for 5, because you've got the 2 in front. You could do it for 9, 10, and that's it. Right? So limited cases, but still pretty cool. Yeah, 3, 4, and then 9, 10, it would work for. And all the questions on the next page, but they use the factor theorem. So what's the factor theorem? Oops. And we've already used this to say, hey, we use long division to probably to factor stuff. And we've even used it just before, right? When we use the quadratic formula to factor something, right? We found the zeros and then we said, well, I can convert that to a factor. And so the factor theorem says that C, right, is a 0 of P, meaning it crosses the x-axis, right? So is a 0 means crosses the x-axis if and only if, which it might be good for you to know that if and only if, we usually just write IFF, if and only if, in math. So if you see that, or you know, when you keep going, it's pretty common that we just say IFF, if and only if. X minus C is a factor of P of X. And so X minus C, if we're able to pull it out, right, and it's a factor of P of X, then at C, it's going to cross the x-axis, right, which we've used because the quadratic formula finds zeros for us. And then we said, well, if C is a 0, then it's going to cross the x-axis there. And then we did kind of x minus the 0, which kind of, for crossing at 2, right, we said x minus 2 is a factor of that formula. Let's do an example so you see what I mean. Should we do, sure, we can do, let's do, yeah, sure, 55. Making me do the hard ones, huh? Like, no. $55 says that P of X is 2x to the 3 plus 7x squared plus 6x minus 5. And we have, just to make sure, right, x to the 3, x to the 2, x to the 1, x to the 0, so they're all there. So I don't need to make any adjustments. But now I want to show that C equals 1/2 is a factor, or we want to show that x minus 1/2 is a factor of P of X. Okay. We haven't dealt with fractions in there, right? But we can handle it. And so here we go. I'm going to put it on its own page here. X minus 1/2 I'm almost tempted to use 0.5 instead. Might work out, right? Might look a little cleaner at least. I think could be risky business. That's okay. Give it a go. 2x to the 3. That's right, because if x minus 1/2 is a factor, right, we use this as the divisor d of x to show that it's a factor of p of x. So what did we say? 7x squared plus 6x minus 5. Okay, we'll do the same thing. How about I'll see you on the other side of this thing. Womp womp. 0. But what have we shown? That means that we're able to pull out x minus 1/2 from this thing cleanly, right? No remainder, which means it is a factor of this thing, right? And so here, this is saying that r of x is 0. Since we do not have a remainder, we have shown that x minus 1/2 is a factor, and maybe I'll write it like this, x minus 1/2 in brackets, is a factor of, and I'm going to cheat and write p of x, because it's that big one. So from here, right, the factor theorem tells us that c equal to 1/2 is a 0 of p of x. So p of x crosses the x-axis at x equal to 1/2. Right. So that's what that blurb is saying, because it's saying that c is a 0 of p if and only if x minus c is a factor of p of x. So if you're able to pull out x minus c, then you can say with certainty that this thing crosses the x-axis at c. Right. Probably more than just that point, right? So let's do 56, where we're actually given 3 and -3 to check. But I mean, we can check with Desmos if you want to do. Now I'm really into uncharted territory here. Did not check these, but here we go. 2x to the power of 3 plus 7x squared plus 6x minus 5. Hopefully this point is at 1/2. I'm really hoping here. Right. So that's what it looks like graphically, right, where it crosses the x-axis. That's a 0. Nice. Okay. Should we do 56 as well? Emphatically, yes. Let's do it. So we've got p of x is x to the 4th plus 3x to the 3 minus 16x squared minus 27x. Wow, they really went all out. 27x plus 63. And c is equal to 3 and -3, which means we're gonna have to divide this thing twice, right? Once for c equals 3 and once for c equals -3. What? Okay, here we go, right? Because here, let's just double check. X to the 4, 3, 2, 1, 0, great. We'll need to divide twice, right? First with x minus 3 and then with x minus -3, which is x plus 3. And remember, to show that it's a factor, right, we're hoping for a remainder of 0 at the end now. Right? So we'll do the same thing. I'll meet you on the other side. I'll start with x minus 3. Let's see. Probably.
Or could be both. No, could be both.
We'll do the second one just to make sure. But what I'm guessing is we'll have some sort of kind of parabolic shape, right? Because it's a fourth power, right? So it should look something like a parabola. And x minus 3 is a factor of p of x. Just write a little note for later. Let's try x plus 3. The only thing that really changes here is the sign for some of these, right? But they'll kind of flip back and forth.
Well, if they did something wrong, they both have to.
Well, that's pretty good because, yeah, it's nice when they both work out, hey? Means the likelihood of having done something wrong is pretty low, right? All right, here I go. Here I go again on my own. X to the fourth times x to the 3 x plus zero. Plus 0x to the 3. I think we can still keep going, right? 0 divided by 0x to the 3 divided by x makes just 0, right? Let's just keep going and see what happens. I'm glad we're seeing something like this. I hadn't really thought of it, but obviously it happens. So here, 0x to the 3 divided by x plus 0 x squared technically. Yeah, I put the x squared on there. It doesn't actually matter. It's just a placeholder, right? So that, because what you'll notice is that all these x's always decrease, right, by 1 as we go through. And let's see here, 0 times 0 is 0, x to the 3, and then 0 x squared plus 3 is 0 x squared. Here, we're going to shake these zeros. 0. Negative 16 minus 0 minus 16x squared. Cool. Okay. We're out of that rut. Just keep going. Oh, I messed up my colors, didn't I? There. Negative 16x. Negative 27. X. Plus 63. Oops. I think we did it, guys. Therefore, C equals negative 3 is also a 0 of P of X. Nice. We can check it in Desmos. Let's do it because why not? What did we have? We had x to the power of 4. Oops, not 1. Haha. Back. No, back.
It took me forever to figure out how to write something to not the power of 2 on here, which is weird because it's right next to the power of 2.
It actually took me a long time as well. I'm like, there's gotta be a way to, I was over here in the functions.
Yeah, that's what I was doing.
Yeah, definitely. But then once you see it, it's like, face palm emoji.
Right next to the square.
It's right there. I know. Been there. 3x to the power of 3 minus 16x squared minus 27x plus 63. Okay. So here, these points are where it crosses the x-axis, right? So it looks like we could have checked 2 other points, right? But it looks like here's negative 3 and here's positive. Oh, here's positive 3. Right? We could have checked these nasty points too, but let's not do that. Right? Nice to check the nice points. Right? Cool. Feeling better? Maybe a little bit. Once you have the mechanics down, then it's just tedious, right? But I don't know about you guys, but I like when things get tedious because then it means I know what I'm doing and I can just kind of do it. All right, let's get into 3.6. So what I did for 3.6 was, and I think I mentioned it last day, but on the last page, right, or it's just the second page of 3.6, I took the question from the final exam. I blurred out the function, right? So it says question 6, neatly sketch a graph of the rational function. So I'm on the second page here. of y equals f of x equals blank. Okay. And then for practice, you can just use any one of the functions in the right-hand corner, and then to go through and answer all these problems, right? Sometimes they'll apply, sometimes they might not apply. It depends on the question. Of course, for the question on the final exam, they're all going to apply and you're going to work through them, right? But this is just for us to practice. And so when you get to the final, it's not like, what's going on here, right? And so so that's why I kind of smushed it all together on one page, and then you can work through these parts and just get really good at all this stuff. And you can check all your answers in Desmos, right? So we're going to talk about things like asymptotes and intercepts, x and y intercepts, and just things like that. So 3.6 is about rational functions. So a rational function, r of x, is just any p of x over q of x. But now the difference is that q and p, right, have no factors in common. So they're as simplified as you can possibly get, right? P and Q have no factors in common. Meaning they can't simplify any further. Therefore, can't be simplified further. Yeah. So just stealing these boxes from the handouts that you've got. Let's talk about some asymptotes. So what's going to happen is if q of x, we've talked about the domain of a function, right? And so if q of x equals 0 at some points of x, what's going to happen is, well, this function doesn't exist at those points, right? And so what you're going to have is these vertical asymptotes at those values of x. And so those look like these guys here, right, in the top row. So here at x equals a, for example, right, we've got this kind of hole in our graph, but how it behaves is the function just kind of takes off and never touches that point, because that would be dividing by 0 and it just can't be done. Same thing on this side, right? It could be approaching from the right or from the left, this vertical asymptote, or it could be approaching from the left and going down, right? Could be approaching, sorry, I said left, but I meant the right. Approaching from the right and going down. Approaching from the left and going down, right? And so we use this arrow notation. So I'll even zoom in on it even more here. In this case, y, these values, are going to positive infinity, right? Because they're just going to keep going and going and going. So y goes to positive infinity as x goes to a. So as x is getting closer and closer to a, right? From the right. It's not very clear here, but because I'm so zoomed in, right? But there's a little plus here saying from the right, right? Or from the positive side. Here, same thing, right? Y is going to positive infinity as x approaches left, approaches a from the left. Is that superscript negative? Okay, so let's write little notes about it. And I think I've even got a little in the box below. I've got what we just said. X approaches A from, and then a superscript negative. Means that it's approaching from the left, and then as it approaches from the right, we put a little positive, right? Or from the positive or negative direction, whichever way you want to think about it. And then if it's curving downwards instead, right, same thing, then y is going to negative infinity as x approaches a from the right, or as x approaches a from the left, it goes to negative infinity. They're going down. And those are our only options, right? But these a's tell us that we've got an x minus a as a factor in the divisor. Okay, so kind of vertical asymptotes happen when the divisor q of x is equal to 0. So tying that back to what we were just talking about, right, with factoring and zeros and all that kind of stuff, we can say that if we have a vertical asymptote, which I'm just going to write VA, usually we just abbreviate to VA, a vertical asymptote at A, right, at some value A, like we've been seeing in those examples or the illustrations. So if we have a vertical asymptote at A, we know that x minus A is a factor of q of x. In fact, if it's the only asymptote, then usually q of x is just x minus A. Right? To summarize, right, just saying the same thing but in a different way so that it hopefully makes sense. So we will have vertical asymptotes at any point of x that makes us divide by 0. Oops. So if we have a look at some of these examples, right, I only gave you a few numbers, right, but that should be plenty to work through all these, right? And so just very simply, let's have a look at 43, which is just 4x minus 4 over x plus 2. This is saying that when x is negative 2, and that's the only place that I'm concerned about here, right? X plus 2 equals 0 when x is negative 2. Therefore, we will have a vertical asymptote at x equals negative 2. And that's the only place that we're going to have a vertical asymptote. And so to sketch this graph, right? What we're going to do is we're going to figure out how this thing behaves as it approaches -2, right? So using things like -1.999, -1.99999, right? That kind of thing. As it approaches it from the right, -1.9 is to the right of -2. -2.01, right? And get closer to it from the left-hand side. Yeah, easier to visualize. And so to figure out the behavior of 4x minus 4 over x plus 2 as, oh, sorry, I should say not at, but as x goes towards -2, right? Because remember, the function could either shoot up in the positive direction or go down in the negative direction, either from the left or from the right. So we have to check all of those points, right? And so to figure out the behavior as x approaches -2, sorry, we usually make a table of values. So what I'm going to do is I'm going to have as x approaches -2 from the, let's start from the left and then from the right. So from the left, and then as x approaches -2 from the right, just to show what's going on here, right? I've got my XY axis here. Here at -2, what I'm going to do is I'm going to pick a couple of points here, 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 right? This is as x approaches 2 from the left, and on this side, we've got x approaching 2 from the right. So it might be helpful to kind of map out a number line to see how, because especially in the negatives, right? Coming from the right means that we're going to be coming from smaller values, whereas on the right-hand side, if we're coming in from the right, we're coming from bigger values, and then the left from smaller values, right? So it's going to be, you're going to want to map it out a little bit, I think. So as x approaches 2 from -2 from the left, right? Let's pick a couple of values of x and 4x minus 4 over x plus 2. Well, if I'm approaching -2 from the left, I can do things like -2.5, -0.05, or even closer, right? Maybe let's go closer. Let's do -2.01. Only because I don't want to be doing a ton. -2.001. Right. Hopefully we'll have a pretty good idea by that point, but it might take a couple more iterations, right? Getting closer and closer. But hopefully we can see if the behavior, because all we're looking for is if we're approaching the positive infinity or negative infinity. Right? And so here, if we use x equals -2.5 in that function on the right-hand side, 4x minus 4 over x plus 2, we get 4 times -2.5, minus 4 over -2.5 plus 2. And of course, use your calculator here. Negative 2.5 times 4. I'll just do it on mine here. Negative 14. Divided by negative 0.5. I get 28. Is that what you guys got? Try another one. 4 times negative 2.01. 4 times negative 2.01 minus 4 divided by negative 2.01 plus 2. Already, I'm starting to suspect that as x approaches negative 2 from the left, I'm approaching positive infinity, right? It seems to be increasing without bound. I'm going to do the last one just to make sure. Right. So I've got 4 times negative 2.001 minus 4. Negative 2.001 plus 2. Oops. Negative 2.001 plus 4 divided by. Right. And so this looks like y is approaching positive infinity as x goes to negative 2 from the left. I'll move this as x approaches negative 2 from the right because I still have to check it down here because I ran out of room. But also maybe I'll put this here and stretch it a little bit. So now if I'm approaching negative 2 from the right, then I'm coming in from negative 1.9, negative 1.99, right, and so on and so forth. Maybe let's start at negative 1.99 and then go to negative 1.999. As long as we can convince ourselves that we've figured out the behavior close to negative 2, then you don't have to do that many, right? You'd have to do more than 1, but 2 or 3. And because my page ends there, I'm only going to do 2. How about? So I'm going to do x is negative 1.99 and negative 1.999. And I've still got 4x minus 4 over x plus 2. Squeeze this in here. 4 times negative 0.99 minus 4 over negative 1.99 plus 2. Looks like negative 1196. Same thing. And you don't have to show this work necessarily, right? You can just give me the answer. I just want to show you where these numbers are coming from, right? And so, but I know it's crowded and yeah, you don't have to show it. Times 4 minus 4 divided by. looks like it's going to be decreasing without bound, right? Meaning that y is going to negative infinity as x is going to -2 from the right. So in terms of what that's going to look like on our graph, right? Because if you have a look at the question, our end goal here is to figure out all the components that we need in order to sketch a reasonable graph of this thing, right? And so the first thing we're going to look at is the vertical asymptotes, right? Usually a pretty good place to start. And so if we're looking at this, what we've just figured out is that here's our x, here's our y. Here at -2, we've got this vertical asymptote. And we don't know where it's going to be kind of centered on, but let's assume it's centered on the x-axis for now, right? Because we haven't done any work to figure out where it's going to be kind of, I call it centered on. But in general, what it's going to look like as we're coming in from the left of -2, it seems to be increasing, right? And so it might look something like, right? But then as we're coming into -2 from the right, it seems to be decreasing. So it might look something like this. Right? But at the asymptote, at the vertical asymptote, because we're going to have horizontal asymptotes as well, potentially. At this vertical asymptote, this kind of behavior is what we're expecting to see, right? Kind of going up, going down, and they're splitting. Nice. Cool. So in general, that's how we would sketch our vertical asymptotes. I'll bring in this next box here because it's actually kind of interesting. So if you have any rational function can be written this way, right? Here up top in the numerator, you've got some polynomial. Here you've got another polynomial. Polynomial degree n and a polynomial degree m. Right? Depending on how n and m are related, so if n is less than m, then what we know is that this huge thing is going to have a horizontal asymptote, meaning a horizontal like this. You remember how I remember vertical and horizontal? Horizontal is because the horizon goes like this, right? So that's how I have to remember it, because it goes like this. So horizontal asymptote at y = 0, right? Which is what we kind of defaulted to here. We said, well, it looks like this guy goes here and this guy goes here, right? Making this a horizontal asymptote, right? Or another option, if n is equal to m, meaning we have the same degree up top as we do on the bottom, then we have a horizontal asymptote at a/b, the coefficients in front, right? We can just ignore everything else and look at a/b, and then our graph will be shifted up or down a little bit to a/b. If n is greater than m, meaning the degree in the top is larger than the degree in the bottom, which is pretty common, then R has no horizontal asymptote, right? Then it'll just kind of, it might have a vertical asymptote, but it might look a little bit weird. So here, what I want to highlight is that These are for horizontal asymptotes. If we go back to the first one, the question that we're working on, right? Our itty bitty little guy, 4x minus 4 over x plus 2, right? The degree of the top one is 1, degree of the bottom one is 1. And so we've got the same degree here and here. And so what this thing says is that if they're the same, then we have a horizontal asymptote at A over B. In our case, A was 4 and B is 1. So now we've got a horizontal asymptote at Y equals 4 over 1 or 4. Oh, okay. So in 4x, now I can't remember what it was. 4x, thank you, minus 4 over x plus 2. This has degree equals 1, and this has degree equals 1. And A1 or A, let's just say A1, oops, in this case is 4 and B1 is 1. The degree in the numerator is n, so that's 1, and the degree in the denominator is m. So what we can say then is that since n equals m equals 1, right, they're all equal to 1, we have a horizontal asymptote. We have a horizontal asymptote at y equals a1 over b1. Well, the subscript 1s are just because the degrees are 1, right? You could ignore them. You could just say a over b, which is going to be 4 over 1, which is 4. So now we can adjust our sketch. Right? We can adjust our sketch to look like this. So let's say that here, this is at y equals 4, just to get it on the graph. Now I've got a horizontal asymptote, which we can call HA. And I also have a vertical asymptote somewhere here. Well, I guess I should move it over a bit. Make it a little bit to scale at least. At -2. So now, instead of going from here and here, right, that would be a horizontal asymptote at y equals 0. Now we're going to go from here and here, right, because we've shifted to a horizontal asymptote at y equals 4. And this is a vertical asymptote. So what it might look like is something like this and something like that. We can check our work so far in Desmos, right? There's a couple of other things that we haven't had a chance to look at, but that we'll look at next day. So if we have our little guy here, I'll put him in brackets, 4x minus 4, all divided by x plus 2. Right. If I kind of zoom out here, so far so good, right? Because, well, I guess I have to figure out, looks like 1, 2, 3, 4. I wish I could draw on here, right? But I can't. Here's 4, which looks like that might be our horizontal asymptote as x goes to infinity, right? And same thing here, y equals 4. Right? If we zoom out enough. And same thing, it looks like we've got this under control where we figured out how it behaves as x goes to -2. So we'll keep working on that, but we're all out of time. Any questions? No? So have a look at those problems, see if you can kind of get the other parts under control. And we'll see you on Tuesday. Yeah. All right.